on to our next lightning speaker. It's Dr. Jesus Barraza, who's a consultant with Neo4j.
Thank you. Well, yeah, as Nigel says, I work for Neo Technology. It's a very nice property graph that shows who I am and who I work for. I mean, interesting because I'm now working for Neo, but I have a background also in semantics and RDF, both modeling and some research experience. So I've been lucky enough to be on both sides of the graph spectrum, if we want to call it like that. So what I want to talk about today is again no sales pitch at all. It's just a very particular topic, which is about semantics, and I'm quite interested by that because it's a term that's used very loosely and sometimes in ways that don't have the same semantics. So I want to understand what do we mean, what the people mean, what the analysts, what the vendors mean, what they say semantics. Also, semantics tend to be associated with RDF and with OWL, RDFS, etc. So I asked myself the question, semantics on graph databases, is that a thing and is that worth exploring? And well, I'm going to actually explore it. I'm going to run hopefully a 5-minute experiment on adding explicit semantics to a graph database, and then we can ask questions or think we can go from there. So a very quick show of hands so that we are all aligned. What do we mean by semantics? So I don't know if that's readable. I'm sorry because that's put too much text. But I have a number of fragments with very small data snippets. I highlight the syntax that's being used, and my question is, raise your hand if you think the first one is semantic. Is that semantic data? These are two triples expressed as RDF turtle, saying John Smith lives in London, and London is a city in England. Is that semantic data? Is that non-semantic data? I would say RDF turtle, no opinion. You would say that's semantic, right? Second one is a JSON fragment. It's a document. We'll have a property called John Smith, and then lives in, and then another sub-document that says London connected to England. That's pretty much the same information. Is that semantic? Yeah. Yes. Okay, good. Right, so third one is Cypher. Cypher is a query language for Neo4j, and again, we are saying the same thing. So we're creating a node, a resource, that's John Smith, that lives in London. Pretty much the same information. Is that semantic? Yeah. Okay. No. Some people say no. Who says no?
None of it is.
None of them are. Good. Okay, so none of them are semantics. Good. Yeah, no, I'm with you. So third one is RDF. Just RDF serializes XML. I'm using very weird terms there. And my question is that semantic? Are there semantics in there? That's, again, a triple. So we're talking about something that has a property with a very weird value. So that's semantics. Probably you think that that's not semantic. Okay, good. Third, the one here is RDFS, because it combines data with an ontology. So here I'm adding to the fact that that this John Smith lives in London, I'm saying also that the domain of the property lives in is location and the range is location. So I'm adding an extra bit there. Is that more semantic to people?
Yeah.
Good. Well, very aligned. And the last one is CSV. Is that semantic? It's pretty much the same information again. So we have a table that has people and where they live, and then some kind of relation between. Right. Okay. So probably they're all semantic. They all mean something. They all mean something to people. Otherwise, you wouldn't express it. You wouldn't even express it. I think that the relevant question is not whether that's semantics. Is whether are the semantics explicit? Because that's the thing to me. That's the key question. And well, that's what I would like to talk about. And again, just wanted to create a little bit of controversy here. Of course, none of the vendors in this room. Not all the vendors, right? So you go to YouTube and see these quick videos or even papers. There's even analysts that create some confusion around that and say, well, you have two facts. John Smith lives in London, and London is a city in England. So you express that probably in triples or whatever you want, however you want. Then you ask a question: who lives in England? And you can express that in Sparkle if you've used triples, or you can use any other query language. And then some magic will happen, and you will get nothing, because no one lives in London, unless ask yourself, of course, what's going on, because there's a little detail missing here. So if there's some knowledge, some semantics that say that if someone lives in a city and that city is in a country, then we can derive that this person lives in that country. But that won't happen unless you explicitly, and that's the key thing, unless you explicitly express that knowledge, that semantic. So, of course, you will use something like this. You will say maybe a rule that says if someone lives in a city and the city is a city in a country, then you can infer that other fact. And then with the combination of that plus the other facts, I mean, you will get the right answer to your question. So the key thing, and that's what I wanted to talk about today, is that making the semantics explicit is what actually operates the magic, if there's any magic, right? And that can be a rule, like I show there, or you can say, well, I'm a purist, I don't write rules because that's not elegant. What I do is I use very well-defined primitives, like inverse functional, domain, disjoint, etc., etc. And there will be a general-purpose engine that will do the reasoning for me and basically infer the same thing, and that's absolutely fine. And you can say, well, city in is a relationship that's stated between two locations. I mean, you can say that a city is in a place, in a country, and that means, basically, that in, again, RDFS terms, using RDFS, that the domain of that property is a location, and the range is also a location. So if you ask a question, like what locations do we know, even though we haven't explicitly said that this is a location, because I've said that London is in England, and I've said also that there's a domain and a range for that property, I can infer that both London and England are locations, right? So, and that's what I mean by semantics. I mean, explicit semantics, that's the key thing. And I've got a bit carried away with the animations here, but this is our friend Tim Berners-Lee. And if we come back to the origins, what he said, I mean, there's no magic, there's no AI. I mean, the whole semantic web, the whole RDF is about us, making the extra effort of making that explicit, right? Making the information understandable and usable by machines. Okay? So just this code, I think that's quite relevant. So an example with a bit of code. And we're going back again. Sorry about the animations, but you can't stop once you start. Right. So we have this implicit semantics scenario. So I don't know again if it's readable. Again, we have our two triples. John Smith lives in London. London is a city in England, and we have an application, right? An application that queries our graph database, RDF triple store. And I want to find which are all the locations, and I can express that in Sparkle, right? And that Sparkle will be give me anything that's explicitly stated as a location, or give me anything that's on the right-hand side of lives in, or anything that's on the left-hand side of lives in, or city in and city in, right? On both sides, as we've seen before. So you can basically enumerate and query your data and get that information, get all the locations in your database. Again, I mean, you have the answer there, but there are no explicit semantics there. I mean, you're querying a graph database, but all your semantics are here on the client side. Is this red bit here? Okay. So how do we move to explicit semantics world? More animations. So we still have our facts there, and I have the two versions, the one rule-based and the one ontology-based. We make these semantics explicit, right? Whether with a rule or with RDFS, formal language, or OWL, whatever you use, and you will have some general purpose engine, whether that's a forward chaining, backward chaining engine, if you use rules, or even an OWL reasoner. I mean, you choose your architecture or your approach, and then the application will just need to ask, give me all the locations, and then the logic, these explicit semantics are kind of in your data. Okay, so we're moving from this situation where you have the data and the logic on the application, the semantics on your application, to moving that to your data store, right? And well, that's where semantics are explicit. And well, that's my question does that have to be RDF specific? Does that have to be OWL specific, right? So in general, I mean, to me, a semantic database is again, that's what we've seen so far. I mean, typically graph databases, and often the RDF model. But, and that's my question, probably not only the RDF model. There must be some explicit description of the data. Otherwise, what you're doing is you're querying a graph. There's absolute value in that. I'm not saying there's not, but that would not be, at least in my opinion, and you might disagree, using explicit semantics, right? And well, these explicit semantics, of course, we know, all heard of RDFS, OWL, etc. But do we need that? I mean, does it have to be that? Do you use that in the first place? Because I have my experience as well, and I was surprised to see myself in situations where you said, are we really using ontologies? Are we using reasoning? Or are we just building a graph model with RDF? So that's going to be my next question. Do we need all the semantics in OWL, in RDFS? And you will, of course, need some kind of often rules-based, domain-independent, genetic processor that applies these explicit semantics and use them in any way. Right, so since that's my view of what a semantic graph database is, we have two consequences. So is my database still semantic if I just use RDF, but don't make my semantics explicit? What will you say? Raise your hand if you say yes. Raise your hands if you say no. Okay, good. I agree with you. So no, but it's a graph, and you're taking advantage of probably what are the key elements in RDF. So because, I'm not here to say that we're two different worlds, I probably started saying that, but it's much more what we have in common. Both worlds, the label property graph, the graph database as well with the RDF world, and it's the fact that we model data as a graph, and there's genuine value in that. So this is like the first consequence, and the second one is, is RDF. Well, not the only way to build a semantic database. Well, do you think there's another way? I'm going to try to prove that it's not the only way. There's other ways. And that's what I'm going to try to show you today. Right. Also, of course, RDF doesn't necessarily imply triple stores even. So if we again go back to the origins, and RDF is a model to represent knowledge, to represent data in a way, basically in a way that it can be exchanged and can simplify integration. So you can still use RDF. I'm not saying again, I'm not trying to build a barrier that separates the two worlds. So you can use any other type of store, and that's the case. You might be familiar with things like D2R or data virtualization. You can expose your data as RDF, even though it's not stored in a triple store. That's absolutely fine. So, and even the whole linked data philosophy, if you want, it's all about how you expose your data, how you link your data, not about how you store it, right? And again, I'd like to come back to our friend Berners-Lee. Most of the success of the RDF is how much of our data we manage to make public as RDF, right? So there's also that. He talked, of course, about relational databases. He said that in '98. So at the time, now we talk about relational, any kind of data store. Exposing it in RDF, there's value in that. And so all these terms, linked data, semantic data, graph data, the important thing is we're all graph data, right? Two different models, okay? You represent the data as RDF, or as a labeled property graph, but then adding explicit semantics, and that's what I'm going to show you in a minute, is, up to you. If you have a language with the expressivity to represent these semantics, and you have an engine that can then use them, there you go. So next step for me is going to be build, I still have 5 minutes hopefully, a semantic graph database in around 5 minutes with Neo4j. So what I'm going to do is I'm going to learn an ontology out of a data set. I'm going to formalize that ontology, make the semantics explicit, of course, and that's my expectation in terms of this time. The first thing is 3 minutes, 1 minute, and the last one is use these semantics to drive some application in an intelligent way to take advantage of these explicit semantics. So what data am I going to use? So I have a set of 230K article summaries from the Financial Times. That's the structure that they have. It's data from 2011 to 2015. So for every article, we have the date, we have a title, we have a URL. At this point, there's a number of keywords, so they're already tagged. These articles have already been tagged. I'm not going to go into the natural language processing or anything. That's not what I'm talking about today. And they have description and a summary. But the key for us is keywords. That's what I'm going to use. So let me now show you my Neo4j instance. Again, I'm going to make that a bit smaller. So what does my, I'll save you the process of loading the data, because it's pretty straightforward. As you see, the structure is simple, but the model that I've built is something like this. Is that readable? Probably not. Well, it's pretty simple. So we have the green circle, the green node at the center is the article, An article has a title, in this case, title here, and it's connected to a number of keywords, and that's the tagging that has been created by the Financial Times when they publish the article. So I've modeled these, all these keywords, all these, as separate nodes, and I've connected them to this as keyword property. There are other elements, but I'm not going to go into that for this demonstration. So that's what the data looks like. Pretty simple, right? So the first thing, as I was saying, I'm going to run a Cooccurrence. So while it runs, I'm going to show you the query if you're interested. But basically, what I'm saying, okay, if there's a keyword that's shared by a number of articles, right? I'm going to figure out what's the level. Sorry, if there's two keywords, right, that are used by let me explain it properly. So articles are linked to a number of keywords, right? So what I want to infer is the level of co-occurrence, how many articles have two keywords in common, right? So that's what this cipher expression, it's a very naive approach to learning an ontology. You can be much more clever than that, but this wouldn't fit in 5 minutes, of course. So what I'm running is this query, and what's producing is exactly that. So Cooccurrence computation, look at co-occurrence. So that's what we produce, right? So we've created connections between keywords based on the fact that they shared a number of articles. So there were a number of articles that were tagged with the same keyword. And I've computed this index, which is a very naive percentage again. So it's the number out of the total that are shared between them. So out of 75 articles tagged as energy, how many of them were also tagged as waste? Well, that's how you compute these indexes. So we have a first idea of how often these keywords are used together. And based on that, I'm going to infer that two things are the same. I'm going to run it. Two tags basically are the same. And the way to do that, sorry about the size of the screen, is very simple. I mean, if you look at the cipher up there, I'm saying if two keywords happen to have a co-occurrence factor of 1, which means every single article that's tagged with this keyword is also tagged with this other one, and the same way around, well then it means that probably these two keywords, at least for my data set, they are the same. And I'm going to say, well, they are the same. So, of course, this is based on my training data set. And I understand that this is not a formal ontology that I'm building. So what have I built? I built something like that. Let me turn this off. And that should bring us. I've made a mistake of running it before turning off the auto completion. So view same as. There we go. So we've created, let me zoom out, a number of clusters of keywords that happen to have the same set of articles tagged with them, right? So again, a simple approach, but what I'm going to do with these clusters is I'm going to simplify them by creating just a single node that groups them all together, right? Making sense so far? Good. Okay, so I'm going to collapse them. That's what this rule does. Again, if you're interested in the code, I'm happy to show. But basically what I'm doing here, all the articles that pointed at all these three, and they all point at all three of them, because that's why they were clustered together, I'm going to make them point to one of them in order to get rid of the other two. Basically create a super tag, right, that contains all the articles tagged like that. Okay, so I'm going to clear the co-occurrence to rerun again based on the super tags. So one more, I'm going to run the co-occurrence computation, exactly the same I ran before, but now I have a smaller set of keywords because I've grouped together some of them, right? And next thing I'm going to do is infer a narrower than relationship, right? So now I'm not going to infer something is the same as something, but if similarly, if all of the articles tagged with one keyword are contained in the other one, but not the other way around, that it means kind of a narrower than a relationship, right? So what I'm doing is constructing something that looks like this. Let me put use it to remove transitive closure. And I built something that I call the ontology, which looks like that. Okay, so these are the tags, the keywords, but linked together based on the fact that they share, well, we've all seen the process, right? They share articles, and therefore they are related. And I've related them in this narrower than, which is a very kind of, it's not a very formal one, it's not a subclass of, it's not an all, if you want, strict semantics, but it can be useful in certain scenarios, and we can look at with some detail at this ontology. For example, we can pick one example just to see what kind of things we've learned from the data. We see that we have a tag called industrial news that has a tag that's narrower than that, which is news headlines, that has basic resources, that has aluminium. So again, these look terms that seem related. It kind of makes sense, right? So that's the ontology. And again, I don't want to be formal. If you're interested in more formal, I give you a reference right at the end of the. And another example here. Also remember that correlation doesn't mean causation. Is that how they call it? So the fact that under corruption we have China or Beijing or anything is just based on the fact that in this data set, well, all the documents or most of the documents that were tagged with China were also under the keyword corruption, right? So that's what I mean. It's not a formal ontology. It's an ontology that expresses the semantics that are probably relevant for my domain. So that's it. First part, probably a bit longer than 3 minutes, but I built an ontology that I'm going to use. It's formalized already. Formalized with this. I'm not using RDF. I'm not using OWL. I don't need that for this problem. I just want to make this explicit. And once I have it, the next thing I can do is, let's see if I can query my data looking, for example, for technology news, right? So is that what I'm doing here? No. That's my query. So I'm looking for a keyword that's IT company news, right? And I get this set of articles that have been tagged with this IT company news keyword. So what I'm going to do now is I'm going to say, let's create 2 new articles. Let's add a couple of articles. That's what the article creation looks like. And I'm going to tag them as IT company news, right? So that's the syntax, but basically what I'm doing is I'm creating 2 nodes with some titles and text. It's Neo4j talking about semantics in graph databases, and Graph Connect San Francisco taking place, blah, blah, blah. And I'm tagging both, as you can see here, as having one keyword, right? And this keyword is IT company news. So if I create these 2 new facts in my database, what I've created is pretty much that. So these 2 articles tagged with the, this keyword, as you see, contains a number of, you remember this has been learned by combining a number of tags. So what I've done is, again, not very clever ontology, but I've concatenated them, and one of them is IT news, IT company news. So that's the facts that I have created. So what I want, of course, is my my query to make use of the semantics that I've made explicit, right? Sorry about this small size of screen is killing me. But we can run this query here and saying, okay, I'm looking for internet articles tagged with internet, and because internet, I haven't shown you, but internet is one of the terms that's broader than IT company news. I would expect that to pick it up and use this these explicit semantics that I've built. And in order to do that, I only have to use a general purpose engine, and this function that I've created. The code is available in GitHub. I can share that with you afterwards if you're interested. But basically, I'm passing the keyword that I want to search, and I say yes or no, use inference. And basically what I'm saying is, okay, use inference means basically use the fact that we understand the semantics of that data that are, in this case, just the narrower than relationship. So why are these 2 articles that I've just created being picked up, even though I didn't tag them as internet? Well, because internet, we learned that it was a broader term than IT company news. So my query is taking advantage of that. I mean, I don't know, it probably was a bit ambitious to run the whole process in 5 minutes. Did the whole thing make sort of sense? Okay, right. So, well, that was the demo. So, as I say, I mean, the whole code, if it's not already in GitHub, will be. So, if you're interested, I'm happy to share that. And yeah, well, as I said before, this is a naive example. I mean, of how I've used a very specific semantics. This SCOS, if you want, style narrower than. But if you're interested in more formal semantics, I've written a blog post that you can find there. What I use are more OWL, RDFS, if you want, style ontology. And you can use it pretty much in the same way you would use it in RDF, to check consistency, to infer new facts. I mean, anything you can think as a good use for explicit semantics. So that's it. I don't know if I've used all my time. Probably have. Apologies.